Hi, my name is Nick Waddoups. I'm going to be giving my talk today, Computing Correctness. So just a little bit about myself, because I don't really know any of you, and I'm guessing none of you know me. It'd be kind of strange if you did. But I'm a student at Utah State University in northern Utah. I'm currently working on my master's degree in computer engineering. I'm doing my research in formal verification of computer chip designs. And so I ended up at this conference because I've kind of been interested in C++ since my undergrad. That was one of the main languages that they use at Utah State for the electrical and computer engineering department. And I listened to some podcasts, and one of them said, hey, you should submit an idea for a talk. And so that's why I'm here. So let's go ahead and we can talk about what we're going to cover today. So today, overall, my goal is to introduce you all to some formal verification concepts and what formal verification might look like in C++ and also what it looks like in some other languages. And mainly, I want to get you introduced to some terminology and some methods and concepts of formal verification so that if you go away from this talk, you can look at literature, you can maybe look at courses, you can look at tooling that's available, and you can understand how the tooling works and what some of the nomenclature is that they're using. So hopefully some of the things we talk about today, you can go away and you can just start using right away. So just kind of as a disclaimer, this isn't going to be an introduction to using some cool industrial strength verification tool for C++, because unfortunately such a tool that would work for all of your wonderful projects right now doesn't truly exist. There are some smaller tools that you can use for verifying portions of your code and for verifying maybe specific algorithms or specific data structures. But right now there's not a holistic, you can just verify your whole code base using this nice tool. So that's how it started. And I welcome questions and any thoughts and comments. So we'll start off with just a brief definition. So here, formal verification is the act of proving or disproving the correctness of a system with respect to a certain formal specification or a property, and we're going to use formal methods of mathematics. So some instances of where this is used, both in industry and in academia, is to verify hardware designs. That's what I do for my research day to day. And what we do is we take a look at a chip design and we can apply mathematical methods to prove if that chip design works or not. And you can also prove other cool things like the probability of the chip failing, or you can prove, how long will it take for, some effect to propagate across the chip. Another area where it's used in critical C code bases. Some people I've talked with before who have worked on flight software or rocket software or similar things, they will turn to formal methods to say, hey, I have this code that controls a very important, critical system, and I need to make sure that it works. And so they'll apply these methods to it. And another area where it's sometimes used is in secure cloud environments. So at AWS, they have a provable security team, and for much of their software where they desire, a proof, something stronger than just unit tests that their code actually works, such as their login subsystems and some of these areas, they actually use formal verification to make sure that those components of their system always will work. And so, and one thing you might notice in this definition is that the last part is using formal methods of mathematics. I gotta say, that is a challenge. I did not take a lot of math classes in school. I don't come from a mathematical background. And one of the most challenging things for me about working in the formal verification space is trying to bridge the gap between the code that I write day to day and the mathematics that are often used to present these methods. So we are going to look at an algorithm, which we actually looked at earlier in the week in the keynote. So we're just looking at a binary search algorithm here where the interface for this is that you give it a span of integers and you give it a target that it's looking for, and it goes through and it tries to find that target inside of the array of integers. And so what our expected return for this is that it's going to return an index into this span that's either the target Or if the target is not present in the span, then it will turn 1 plus the end of the last indice. And so basically the same function as something like stood lower bound or another binary search implementation, but we're doing it with indices instead of with iterators and pointers. So what do we know exactly about this? How do we know that this function works? This code appears in lots of libraries. If you look for some binary search code, you might see something that's implemented like this. It appeared earlier this week in the keynote, so that's maybe a good indication that we hope it works. And we also might want to say, what kind of properties do we want to formulate about this specific function? So for example, one of the things that we might want to prove is we might want to say that our return is always correct. And so we might want to say something like, if target is inside of our array, then we're going to return the indice of target. Otherwise, we're going to turn the size of the array, 1 plus the end. And we also might want to say, we have this loop in the middle of our algorithm. How do we know that this loop always terminates? Yes?
I'm so confused. Where do you return the size? Like, it seems like standard low. You say when it's not found, you return the size plus 1, and I don't see it in code. I'm sorry.
Oh yeah, that's all good. No, so this it's because it's a little tricky. So what this does is you return the size of the array, which is the last possible index plus 1. Sorry, I think I messed that up or when I said it out loud. Because what happens here is, so if we have an array, we start by looking at the midpoint of the array. And because we're doing a binary search, we assume our input is going to be sorted. And so if we look at the midpoint and we say, okay, we didn't find target here, and then we're going to go up to the next point, and we should be able to say, after going to the next point, that that target is not there, and then from there we should be able to just continue looking through the array until the target is not in the array. But actually, now that you're saying that, I do think I may see a bug in my code.
This looks very correct. It's just not what you're saying.
Yeah.
Yes, I see what you're saying.
It's lower bound. It's not.
Yes, it's lower bound. So that's my bad. So it would go, so if it's not in the array, then we'll return something else.
The first element smaller than where it would be.
Yes, where it would be, where it should go. Which now brings into question the rest of my presentation about formal methods. So, woohoo! All right, things are going great so far. Great question. So here we might want to prove termination of our function. So we might want to be able to say that, can we guarantee that if you call this binary search function, that eventually it is going to finish? That's another thing. And in your algorithm, you're probably going to have a more complicated looping structure than this. But being able to prove that, hey, we don't ever run into an issue where we reach, a deadlock state or an infinite loop is really great for systems. And one other area we might be interested in deriving a proof for is here we're doing an array access or a memory access where we're indexing into this span. And we might want to check that, hey, does my algorithm ever accidentally index outside of the span? Either to with a negative indice by going in the wrong direction, or with an indice that is greater than the size of the span and going into memory that we don't own. So with all these thoughts and ideas in mind, these formulate properties that we want to define about our system. And so a property is just a statement or a characteristic about the behavior of our system. And when we define these properties, we typically define them as a proposition that we can either say, hey, this property is true or this property is false. And so there's a couple types of properties that we want to look at. So the first is a safety property. And when we look at a safety property, we often want to say that bad things do not happen. And so, for example, if we have a microwave, we don't want the microwave to turn on while the user's hand is inside the microwave. That would be a bad thing. And so we would say that our safety property is that our microwave should never turn on, when someone's hand is inside, or we could extend it to say something like when the door is open. And the second type of property that there are what we call liveness properties. So a liveness property means that eventually something good happens. So continuing with our microwave example, what we would say is that eventually our food is cooked. And we could maybe measure that by checking that our timer on our microwave, continually decrements until it reaches 0, at which point the microwave is done. So if we look at our binary search implementation, we might want to formulate some safety properties, potentially about what does this binary search return, and also potentially about that this binary search always terminates. So how do we go through and how do we formulate these properties? C++ doesn't exactly have a way that we can semantically say, hey, for all possible inputs, for all targets, and for all span over ints, we want this binary search function to work correctly. And so what we turn to in formal verification is we usually turn to mathematics. And mathematics are sometimes scary. So let's look at this first property that we looked at. That I realized if I had changed some of my test cases would actually not have worked. So this is going to be an experiment in some live coding that we'll do in a little bit. But we're saying that our property here that we want to check is that if target exists in the array, we want to return the index of the target in that array. And so if we want to formulate that, we need some way of denoting that target exists in the array. And so in math, we would do that by using this exists operator right here. So on the right-hand side, we have this weird backwards E. And this just indicates that something exists. And we'll walk through a little bit more about how this whole formula works and how you might go through and use a formal verification system to implement this. So, but first we'll just walk through this formula. So we start with the backwards E and then a variable. Yes?
Do I understand correctly, you never indicated there that their input array is sorted in this specification?
In this specification, yes.
Okay.
So this specification is checking that the return of our binary search function is what we expect. But we do need to include a precondition as well. So no, so not in this specification here. So this is kind of already assuming that our input array is sorted. So in this case, we'd kind of consider this a safety property in terms of we don't want something bad to happen. And in this sense, we're saying that something bad would be we return the wrong value. And in this property, we're not going to encode our assumption that array is sorted. But we do have to encode it later to let the proof system know.
So are you assuming that binary search will return the correct result for an unsorted array or not?
No, we're not assuming that. If it's an unsorted array.
This is just an incomplete property.
Yes.
Okay, thank you.
Yeah. I guess kind of the way I think about it is that we have our properties, and typically I think about them as being separate from our assumptions or our preconditions we make. And so I didn't make that clear on the slide though. So yeah, so we have an assumption that array is sorted, and then based off that assumption and our implementation of the algorithm, we want to show that this property holds. Does that make sense?
Sure.
Okay. So yeah, quickly going through this equation here. So we start with the exist operator. So this is a existential quantifier, this is a fancy name for it. And what we're saying is that there is a variable I that exists. And this statement can be thought of as kind of a proposition saying, does there exist an I? And then we'll add some constraints onto it. So the semicolon just means, the colon just means there exists an I such that, and then we can add a constraint on the left-hand side here, and we're checking to see if I exists in that, whatever that constraint is. So for example, if we gave I the type of integer, and we wanted to check here that does there exist an I such that I is between -10 and 3, then this statement would return true because there does exist at least one I that meets those criteria. And that's one important part of the exists quantifier is that it only says that there has to be at least one. There's no guarantee that there's more than one. So this returns true as a proposition. So this also means that we can actually have kind of nonsensical statements in our exist clauses. So for example, here we're asking, does there exist an I such that I is greater than 0 and I is less than -1, which as a statement doesn't really make sense. Obviously that's not going to be true, but that just means that this whole statement evaluates defaults. And sometimes when we have these kinds of issues in formal verification, we run into issues where we accidentally encode these type of statements into our property, and then it can't be proved, and it's kind of hard to figure out why. So let's go ahead and let's look at how we would translate our English definition of our property into a mathematical definition. So first we're going to say if our target exists in our array. So we're going to do this using indices, because that's kind of how our function operates on the values in this array. So we're just checking if, does there exist an I such that I is greater than 0 and less than array.size. So that's just going to mean that I is somewhere on the domain of the indices of that array. So we're not going to go out of bounds. And we also want to check that at that index, I, that array of I equals target. So what this is just saying here is it's saying, does there exist a I such that in our array, that index is equal to our target value. And so now we need to add the return. So we're saying that it returns the index of that target in the array if it exists. So how we can encode that in math is we can say that by calling this binary search function on array and target, we're going to get our index out. And in the middle here, we have this implication operator. So this is a Boolean operator that, at least for me, I did not learn about when I learned all the other Boolean operators. But basically what the implication means is it's kind of like a if then else true statement. So what we're saying here on the left, if there exists an index such that target is in the array at that index, then our function, binary search, should return that specific index. Otherwise, if that index doesn't exist, then we don't really care. It's just going to be a true proposition, a true statement. And so this is a little confusing as to why it should just be true if the left-hand side of the formula doesn't hold as false. But this is because implication is kind of a one-directional thing. So for example, if we said, if the sky is clear, then it's not raining. That just tells us that if the sky is clear, there's not going to be clouds, and so likely it's not raining. Although Earth is weird, so sometimes it still does. But we can't say anything the other way. We can't say if the sky is not clear, then it is raining, because that doesn't necessarily have to be true if it's just a cloudy day. So that's what this implication operator does, is it's this one-way check to say, hey, if the left side is true, then let's see what the right side evaluates to. There's a great talk, if you want to learn more about the implication operator, by Ben Dean. He talks about it in this talk, Message Handling with Boolean Algebra. And he gives really good examples of how you can use the implication operator to prove things. So altogether, this is what we have ended up with for our target here. So we're saying if the target exists in the array, then we want to return the index of target in that array. And then otherwise, we were going to return array.size. But yeah, yes?
Do you mean or and for the second, joining the two?
For this one?
Yeah.
This is going to be an or.
Why?
I guess it should be an and. You're right. Yeah, so it should be an and. Should have had someone review these slides. Yes?
Are you assuming no duplicates?
Yes, in this case, we would be assuming no duplicates. Well, I guess if there was a duplicate, it would just return the first one that it found.
Yeah, well,
So, yeah.
Well, this just says it returns one of them.
That's true. So it would just return one of them. Well, yeah, it wouldn't return all of them. It would just return the first one that the algorithm finds.
Yeah, so you have to say no duplicates, otherwise you can't guarantee I.
Okay, yep, that's fair. So yeah, so we would say no duplicates then.
Oh, wait, you're saying there exists an I where if it's equal, then you return the index.
Yeah.
I guess, yeah.
Which I guess could be a problem if there was a duplicate. You could say that if there exists an I could be, for example, either index 5 or 6. And then when you return, what do you return? Do you return 5 or 6? Because there exists 2 i's. So that's a good question. So, but yeah. All right, so the second property that we wanted to look at was that binary search always terminates. So to terminate this property, there are a couple of different ways that we could do it, but we're kind of going to go into those later today. We're not going to go into them specifically right now, because typically how you prove termination is you need to look at, or you also need to consider the method by which you're going to prove termination. There's not exactly one clear way to just say, hey, I want to prove that this always terminates for any inputs. So, but we're also going to just go over one other operator real quick. So that's the for all operator. So here we're just saying for all x, such that something happens. So for example, if we said x were integers, we could say that for all x, x times x, or x squared, is going to be greater than or equal to 0. And this would, again, just evaluate to true. So now that we've had a bit of a mathematical background on how we formulate these properties, we're going to talk about how tools, yeah.
When you have the equal sign,
Mhm.
Does that also return a Boolean, the whole expression? It's either true or false?
Yeah, I guess you would be a Boolean.
So that whole expression is true.
Yeah, that whole expression would be true. So because I'm saying that,
So couldn't you remove the equals true on the right-hand side there?
yes, that was just for like showing that it was true. So like this whole expression evaluates to true. And so here you've got true is equal to true. So that would work. But yes.
Okay.
So but yeah, now that we've kind of formulated these properties, we're going to walk through a couple examples of how tools actually might go through and prove them. So we're going to talk about 2 different methods that tools use right now to do formal verification. So the first is model checking, and the second one we'll talk about is deductive verification. So first, for model checking, how model checking works is it takes your code and it builds it into a formal model, and then it goes through and it tries to enumerate all the possible execution paths through your code, and it checks if any of those execution paths fail. And so the process that a model checker, the program that does this, how it works is kind of looking like this. So you have your code, it gets encoded into a formal model, it's combined with your properties in a model checker, and then after the model checker is done, it's explored all the possible executions, and then it checks if it's valid or not. And you go from there. And so we're going to talk about some tools that do this. If you were in the last talk, TLA Plus is a tool that essentially does this behind the scenes. And it goes through and it checks all the interleavings of a concurrent program and then tells you if they're valid or not. Mm-hmm.
And when you say valid, is that the same thing as correctness?
So valid just means that your safety properties hold. So if you have correct safety properties, then it would be correct. But if you have incorrect safety properties, then you don't know exactly what you've proven. So yes, I guess valid is the same thing as correctness. Like your model meets all the properties that you provided. So if you said, my property that I want to check is that I never can access memory outside of out of bounds, and then you get to the model checker enumerates all possibilities, and you get to the valid check, then if that's valid, so if you're done, then you'd say that I never accidentally accessed outside of memory that I own.
So if your program is consistent with your properties,
Mm-hmm.
then you'd say that's valid, which is the same thing as saying it's correct.
Yes. Mm-hmm. Yeah. Uh-huh. Yes.
You keep saying safety, and you had both safety and liveliness. Do you distinguish something here, or it doesn't matter in this case?
So in this case, it doesn't exactly matter. So
Okay.
you could check both properties with a model checker. So yeah, your liveness properties as well. If you have a property that says, eventually, my system does something, then this would also be checked by the model checker and valid. So if your code is not valid, if the model checker finds a sequence of executions that do not meet your properties, whether safety or liveness, then it will return you a counterexample. And what a counterexample looks like is a sequence of states that led you to the bad state. So we're going to kind of walk through the steps that happen here inside of the model checker. to see how it works and also to see what some of the issues are that come from model checking. So if we have our code here on the left and we want to check that it's correct, then we need to convert it into some kind of model that a model checker can understand. And so the goal of a model checker is to go through and enumerate all possible executions. And so in order to do that, we have to have some way of checking a state here, continuing on to the next state, and progressing from there. And so what we do to do that is a commonly used method in formal verification is a transition system. So with a transition system, you start with an initial state, and then there are some allowed transitions that you can take, and those transition you to future states. And you can use a transition system to model pretty much any part of a program. And so you can model branching, you can model loop semantics, anything that you want. And so inside of each of these states is just concrete values of what is inside of your program. So for example, if we had here on the left, this was our program, we just had 2 integers and a string, then some example states of what we might see is if we had, for example, state I would be a concrete assignment, 5 and -10 to x and y, as well as an assignment to the string. And so that's different from state J that has different assignments to all the variables, or all the variables. So to enumerate all the possible states, we go through a couple of steps. So first we take our code and we need to convert it into like a go-to style. So we need to remove all of the loops and we need to instead add labels and go-tos. And we do this because then we need to add an additional piece of state information, which is the program counter. So the program counter keeps track of what line we're actually checking on before we progress to the next state. So these 2 steps right here are both part of, in the previous flowchart, converting your code into a formal model. And then after we've done that, starting from the initial states that we can determine from our code, we're going to execute all possible computations, and that will determine the state space of the system, which we'll talk about a little bit more in a minute. And then after doing that, we'll just check if there are any states that fail our properties. And if they do, then our program is not correct. And if there are no states that don't, we've explored all possible states, so our program must be correct. So we're just going to go through this simple example here of how we'd convert this into something that we could then model check, and then what the model checker would do. So first, we're going to take this and we're just going to convert it into our go-to format. And so we're going to remove our loops, and we're going to add a label for our loop and a label for after the loop at the end. And then we're still going to have the same computation of dividing x by 2 every loop iteration. And we're going to just have this different representation of our program. Yes?
I'm just curious, would SSA form be easier for this and that stuff?
Oh yeah, you could do SSA form as well. So both of them would work fine. There are some tools that do SSA form and some that do it like this. So you can use either. Yes?
What's SSA form?
Oh, so SSA form is single static assignment. And so in SSA form, you kind of convert it into a similar thing where you're trying to remove, you're trying to remove like additional programming syntax where you can reassign variables, where you have loops. And in single static assignment, every variable gets just assigned once. And
LLVM intermediate code as SSA form.
yeah. So and you can use that as well because SSA code has as well very like similar semantics that are easy to reason about because you don't ever have variables in SSA where you're taking one value and you're reusing it for different parts of your computation. Instead, you just have variables that are just used in their individual part. So after converting it into this go-to form, we are then going to add our program counter, which is just an additional piece of state. So in this case, we just add one value for our program counter for each line of computation that we do. And then after this, the last step before we can start model checking is we need to determine our initial state. So in this instance, it's pretty easy because we don't have any input arguments that we need to resolve or anything like that. We just start at program counter equals 1 and at x equals 3. So if we look at our initial state, we're just starting here where our program counter equals 1, and after our computation, we're going to have x equals 3. And so this just represents our initial state there. And then what the model checker does is the model checker automatically says, okay, what transitions are possible for me? And the model checker does have a bit of information about what a program looks like. So it knows that typically transitions that I can take are going to be incrementing the program counter, that's going to be 1, or going to be branching to a new location in the code. That's going to be the kind of the second type of transition we can take. So in this case, we're not dealing with any branching. And so the model checker would just say, okay, we're going to increment the program counter and just move on to the next state. So when we move to the next state, we're just going to get to this loop here. And we're going to say, we are checking a branch. But in terms of the states of our program, x hasn't changed, only our program counter has changed. And so here we're going to do the comparison again. We're going to say, is x less than or equal to 0? It's not. So again, we're going to take the possible transitions. And from here on, it's pretty simple. We're going to say, okay, we're going to go to state 3. After going to state 3, or program counter 3, we're going to go to program counter 4. And we can see here that in between these, our value of x updates because we do some computation on it on line 3. And then basically the model checker will just go through this sequence of computations, and eventually it will get to the program counter equals 5, and in this case, x will be equal to 0. And so pretty much the model checker is honestly not that smart. It just goes through and it just says, what can I do next? And then it does it. And in this program, we only have one path of execution because we never have somewhere where x gets assigned to a value that's non-deterministic, or there's no parallelism here, so we're not looking at any of that. So it's just one path where we start from this initial state where our program counter is 1 and x is 3, and then we end at a state where our program counter is 5 and x is equal to 0. So once we have this beautiful trace of all the possible states of our program, it becomes pretty trivial to check properties on it. So for example, we might want to check a safety property that says that when our program ends, we want x to be equal to 1. In this case, we know that x is equal to 0, so the model checker would return us this trace, this sequence of states back to us, and it would say, okay, this can't be true because by the time I got to the end of the program, x was actually equal to 0. And then you could go back through and you could determine where your error lies. So, like I said before, there's only one trace through that program. But often, real programs don't really look like that. Hopefully, they shouldn't look like that. And so, if we change this just a bit, and we change this declaration on line 1 to be that x is the return of some function, now we actually have multiple initial states because we don't exactly know what x is going to be initially. Or you could also think of it as, when we start, after we assign x, it's going to be whatever function returns. And so there's a couple ways that we could handle this. So the first thing that we could do is that we could just say, well, we know that x must be something in the domain of an int, so we'll check every possibility from int min all the way to int max. And that's a pretty bad way because that's about 4 billion different traces that we then have to generate to see if our properties hold. We could also try to inline func to see if we can determine from that function what the domain of its output could be. And we could also just analyze it, maybe by hand, and then indicate to the model checker, hey, we know that this function always returns something within this range, or it returns this set of different values that we are doing. So in this case, we can kind of see where a model checker might run into issues, where you are using a lot of memory or using a lot of time to check all the possible computations. But the good thing about model checking is that overall, it is really highly automated, and you don't have to do a lot besides providing your code and providing a safety property or a liveness property. And then from there, it will go through and it will try to check everything. So the main problem with model checking is, oh yes.
So the way you've described model checker, if I'm not mistaken, is it runs through your program, like with every possible input.
Yep.
Is that how they work in practice, or do they, can they make generalizations of pieces of code and such?
Yes, we'll get there. But they don't work quite that way in practice, because that would be not so useful. So yeah, because the main problem is our state space. So that's the space of all possible assignments to the states that we have. And so, for example, if we just have two 8-bit integers, we immediately have about 65,000 different possible states that we could traverse to from any of these integers. So any location on that grid or on that plot within that blue square represents a possible assignment to X and Y. So a couple things that model checking does bring is we only explore our reachable state space because we're only concerned with where can our program actually end up. We're not really concerned with, what are all possible values of our program. And so then another thing that they do, so these are two C and C++ model checkers that you can use. If you're interested in actually doing some model checking, I'd recommend checking out CBMC. ESBMC is more promising, but it's also got a lot more bugs currently. So I'd consider checking out the other one first. But what they can do is they can do more of a symbolic execution, where states, instead of being stored as discrete values, can be stored as formulas, that maybe represent that your variable is on some range, or that your variable is one of several different choices of values. And so both of these are model checkers that work on C and C++. They can handle real C++ features. You can write templated functions, const expr, auto, and they are able to handle all of that. And then to add your properties to these to your code to use these, they do it in kind of two different ways. So ESBMC basically gives you a custom library where you call these functions to add your properties, and then the model checker sees those function calls and says, hey, I know this isn't actually a function call, this is a property I want to check. And CBMC, you do it through like comment annotation. So you add a comment saying, hey, check that this never accidentally reads out of bounds. So these are great for, two questions.
Okay.
So I'm just curious about UB stuff. So like integer overflows and this kind of things. Will it check those automatically for you?
Yeah, so it will. So most model checkers have a kind of set of things that they already know. And so there are some properties that they will just kind of check by default. So some of those will be things like integer overflow. If they detect that you're going outside of the range of an integer, it should be able to say like, hey, this is outside of this range, that's undefined behavior. You probably didn't want that right here. And with other types, like with pointers, they will automatically do, similar static analysis checks that other static analyzers can do in terms of making sure that you're not dereferencing null pointers and making sure that you own the memory that you're accessing. So yeah, and then Jeff?
How does a model checker usually represent undecidability? Like not just that the state space is big, but like I haven't got an answer for you yet. I don't know if I ever will.
Yeah. So if you give it an undecidable problem, then that's not really checkable by a model checker. And it should just tell you right away that it's not able to check that.
But that's only if it can prove it is undecidable. Like how to,
Oh yeah, I guess.
sort of
No,
like-
it often this is reported by hanging.
Okay.
Yeah.
It
So
says bounded model checker, so these go into a certain number of iterations, and then
yeah. Oh yeah.
they try to
So
increase the number of iterations they go through, but they might never find something.
yeah, so that's a good point. So these ones are bounded model checkers. So they look at a fixed number of iterations. And so, but a lot of times they will try to give you some kind of warning at the beginning saying something like, hey, I don't know if I'm going to be able to do this or not. But yeah, so I guess kind of So a real example of this in my research that we're working on is we're working on verifying a network model. And one of the issues we do run into is that the specific model checker we're using, which isn't either of these because it's a probabilistic one, but an issue we run into is an issue of memory usage. So our network model is pretty big. We're trying to model a mesh network between 9 different nodes and model all the different interleavings and all of the different communications between them. And we do see an issue where we run out of RAM at about 200 or so gigabytes. And then the model checker says, uh-oh, I ran out of RAM. I can't prove anything about your model. And so when you do run into that case, it's a great opportunity to look at it and say, well, I literally can't do anything, so I guess I need to simplify my model. And Malta talked about this a bit in his talk, about how if you run into issues doing model checking, you often have to look for ways to change your model or to tell the model checker, hey, I don't care about these states, go ahead and skip these ones or something like that. So yeah, yes.
Just because I have no experience, how composable is this? So if I verify one function and I verify another function, and I have preconditions on that, so how much, I have a third function that calls the first two, how much of the work has to be redone for the internal function?
So if you can generate a proof for either of the functions, then you don't actually need to usually look at the internals of the functions anymore. So one of the things about model checking and formal verification in general is it typically does compose very nicely if you have regular functions. So as long as your functions don't necessarily depend on a global variable or something, then if you say, okay, I have function A and I have proved that function A does what I want it to do, and then you call function A inside of function B, then function B doesn't need to actually inline function A because you already know what the precondition will be and what the postcondition will be of that function.
So follow up, can you explain why the model blew up to 200 gigabytes, why it wasn't composing?
So yeah, well, it was because we didn't write our model in a composable way. So we specifically laid out all the 9 nodes in our network model. And then so instead of trying to verify that one node just works correctly and that it never runs into any issues, and then composing them together, we just laid out all 9 nodes at once. And when we did that, we thought, it'll definitely fit, but it definitely did not. And then we ran out of memory. And so we went back and we did extract parts out from each of the nodes. And we said, okay, we can actually verify this portion of this node independently. And then after doing that, those smaller checks ran very quickly with very limited memory use. And then we were able to say, okay, given that we know that these smaller components work, we can compose these components together to prove that the system as a whole works.
It makes sense, thank you.
Yeah. Okay, so we're going to talk about another method of formal verification of code. So we're going to talk about deductive reasoning and deductive verification. So how deductive verification works is you start from a set of premises, and then from your set of premises, you're going to deduce or draw conclusions that you can make from those premises. And so the classic example of deduction is Sherlock Holmes, where he looks all around and he sees a bunch of clues, a bunch of premises, and then from there, he makes the great leap to, solve the mystery or, figure out who the murderer was or whatever it is. And so we can use that same type of reasoning to reason about our code. And one of the benefits about it that we'll see is it's actually a lot more composable than model checking is. So the core thing that happens in deductive reasoning is what we call Hoare logic. And so this comes from the computer scientist Tony Hoare in 1969. And he wanted to develop a way to reason about sequential programs. And so this is pretty similar. I'm guessing some of you have probably seen this before, if not all of you, but pretty similar to contracts, for example. So what we have here is we have this math statement that says we have a precondition P, we have a statement S that executes some code, and then we have our postcondition Q. So we're saying that given our precondition, so given what is the state of our system before the statement, we're going to execute some code, and then we'll have a postcondition based off of that. So we'll go through a short example. So if this is our program, just a declaration of an integer, we are going to look at some rules that we would apply in order to derive our precondition and our postcondition after our statement. So here we can say that our precondition is just true. We don't really have any precondition. X doesn't even exist before this line. And our postcondition is just going to be that X does exist. And so when we're considering this, we don't know after the statement executes what X is, but we do know that it's here. And so we build these rules up for every type of thing that you can do in your language. So for example, this would be a rule about declarations, what happens before, what happens after a declaration. So for example, we can go through these 3 super short rules. So we have our declaration, which we just saw, where we don't have a precondition, and after it, we just know that X exists. Yes?
Just a question about your use of the word precondition. So you said precondition can be true, or this is the lack of a precondition. Both of those things mean the same thing, right?
Yes.
Okay.
So yeah, so if you don't have a precondition, you could just say your precondition is true, and that means that you accept any state before this statement if your precondition was just true.
Okay.
So yeah, it'd be like if you wanted to check something in a function and you said, I have this predicate and this should be true before my function, like that's your precondition. If your predicate just always returns true, then that would just mean that your precondition holds for any inputs.
It's kind
So when we talk about pre and post conditions in C++, we often talk about having a list of pre and post conditions rather than a single one. So it would be equivalent to the list being empty.
Yeah, the list being empty. Or if your list, so it would be the equivalent of the list being empty would be anything goes before this statement.
It's kind of like an implication in some sense. It's like saying after running S, like P implies Q. Like P before the statement implies Q after the statement. Yeah,
so exactly. So after running S, does P imply Q? Including S, I guess. So yeah, it's like the implication. So we have these 3 different rules that we can look at. So declaration is just introducing X into our state, but we're not giving it a value. So replacement is what we typically look at when we look at an assignment, although that does sometimes get more complicated. But here we're just saying for our precondition for this specific statement, we don't really care, again, what X is, because after this statement, we're just saying that X is always going to be 3. And so that would be like a replacement proof rule. And then the last statement is incrementing X by 1. So in this case, we do care what our precondition is, because our postcondition depends on the value of X in our precondition. And so in this case, we can go through and we can kind of reason through these 3 statements, and we say, okay, at the end of these 3 statements, we always know that X is going to be equal to 4. And so if we had a safety property that stated that X was equal to 4 after this execution, then we could check it here. And another thing is that we can also check safety properties that are weaker than the ones that we calculated. So when a property is weaker than another one, it means that it allows more behavior. So if we had a property that said something like, you can't put your hand, or the microwave does not run when your hand is in the microwave, a weaker property than that would be the microwave does not run at all. That would be weaker than the vice versa, because anytime that the microwave does not run implies that if your hand is in the microwave still does not run. So we could check that as well here, saying that if X is greater than 0, that's weaker than X is equal to 4. It allows more things, but we can still check that as a safety property. So we're going to look at this lower bound implementation again, and we're going to see how would we actually go through and do a proof on this. So what we would do is first we're going to come up with our preconditions. So we're going to start by saying that our array needs to be sorted. So this is what you were asking about before. So we do need to include those when we're actually going through and doing a proof. But we're going to say that our array must be sorted. That's our precondition here. And additionally, as someone pointed out, we should have unique elements in our array, but we didn't add that, but we can add that. And then we're going to have our postcondition, which is saying that if our target exists in the array, then we're going to return the index of the target in that array.
Instead of requiring, or instead of making it a precondition that they're unique, you could also make it a postcondition that the resulting index is the least such that.
Oh, that would work as well. Yeah, it would be the least occurrence of target in array. So yeah, so that would be another way that we could go through and do that. So we can't really encode these semantic constraints and these deductive proofs in C++ right now. I did look, and there's not really any deductive verification tools for C++ specifically. There are some available for C that you can use. There's a great one called Frame-a-C, which does this process on your C code. But for C++, there isn't really an option out there as far as I could find. So instead, we're going to look at a different language called Daphne. And Daphne is a relatively robust tool, despite what this logo may lead you to believe. So I looked, and there was a GitHub discussion about, hey, maybe we should improve the logo from like 4 or 5 years ago. And anyways, I don't know, the thread just kind of died off after someone suggested some really cool logos. So I'm not really sure how they ended up with this logo. Yes?
Do you know if anybody's tried to like make a rewriter for C++ to C and then use one of the C model checkers on it?
That's kind of what ESBMC does. So ESBMC has like a Clang front end, and then it goes through and it takes all your C++ code, instantiates the templates, does all that stuff, and then it works off the Clang syntax tree. But I don't know if there's anything that rewrites them.
Maybe not rewrite, but we support C++ and it's based on Frame-a-C.
Oh, you
It
do?
does disintegrate the code, yeah.
Okay.
If you're interested, just contact me after. And we
Okay,
can
cool.
talk offline. Yeah.
Cool. Yeah, so I did not know that because I've used Frame-a-C for C code, but I've never tried doing C++ code in it. So good to know. So this is a verification-aware language as well as a tool set that you can use to create proofs about your program. And so you can kind of think of it as a language that comes with really strong static analysis and compile time verification. And then the benefit of that is if you can do all this verification at compile time, then of course when you run your code, you don't need to include checks that you already have proved at compile time. So we're going to rewrite our binary search into Daphne code. And so hopefully it looks pretty similar. There are a couple of syntactic differences, but overall the code does look the same. We'll just walk through them really quick to make sure that we're all on the same page. So in the declaration here of the method, we use the method keyword, which just specifies a function basically. It's actually a little different than that, but the differences are beyond the point of this talk. And we're going to have 2 input arguments, array and target. And so instead of being a span, array is going to be a sequence of int32s. And a sequence has really the same semantics as a span. You have some number of elements, and you can iterate through them. You can get a starting position, an end position, all that information. Then we have a target. And then something that C++ doesn't have that Daphne does do is it has named return values. So here we say that it returns a variable index of type int32. And so instead of just saying that we are returning an int32, it names it. And that's actually so that during our verification, we can use that variable name in the proof. And you'll see how that works in a second. So some other syntactic differences, which we'll just go through super quick, are on like the second line after the curly brace, we can see that there's these 2 vertical bars around array. That's just the length of the sequence. And I actually don't know exactly why they chose that syntax because it's not present for the other data types that are like sequence. For casting, we just have the as operator. Yes?
Just to confirm, the maximum length, is this a cast saying that we are limiting our array size to int32, or the maximum length of the array is int32?
So we're casting it to say that it's going to be within int32.
Okay.
And that's just to match the C++ definition that I gave here, where we're saying that that high is a type integer. And so here, just like array.size doesn't return an integer, I believe it returns a size t. And so it's implicitly getting casted here. Daphne doesn't jive so well with implicit casts. So anytime there's a cast, we just have to explicitly say, hey, I want you to treat this as a 32-bit integer instead of an unsigned. Yeah, and then I think the rest of the code is basically the same. In Daphne, they use the colon followed by the equals for assignment. But yeah.
What happens if the cardinality of ARR is outside of the bounds of what int32 can represent?
Oh, that is a great question. So if we put this into some Daphne code and then we ask it to compile or to verify, it actually goes to this line and it says, I am pretty unhappy with this line. And of course, it gives us an error in a very confusing manner. One thing, at least I found with several formal verification tool sets, especially deductive verification ones, is you sometimes get errors that don't really make sense. And we'll kind of go through why that happens in a second.
This is C++ conference.
That's true. That's true. So I guess I should expect that everyone already knows, because yeah, very similar problems. But the only problem with deductive verification is because it's based off proof rules. Sometimes you get an error that's not actually an error, which we'll go through in a second. So here we get an error, and it says that the result of this operation, and it's indicating that the operation is the cast to an int32, that it might violate the new type constraint for int32. And so that's kind of weird. Like, what is a new type constraint? What does that mean? But really what it's saying is it's saying that int32 has a type constraint that it is, bounded between about -2 billion and 2 billion, and that this operation right here might accidentally exceed those bounds. And so we can say, so this is a problem in our C++ code as well. Theoretically, we could have passed a span that has a size of 8 billion, and then when we try to convert the usize into an integer, we'll have some kind of overflow. So yeah, but Daphne doesn't really like these kind of issues. If you have them, it will immediately point them out and tell you that you need to fix them. In this case, we're actually not going to fix this error. We're just going to tell Daphne to ignore this one because that would change our code more than I care to do at this moment. But for the rest of the issues, we'll walk through how to fix them, and we'll walk through the great things about Daphne showing them. So if we tell it to ignore the first error, then it gives us a second error. So it looks at this computation right here, and it says that the result of this operation, again, might violate this new type constraint. So again, if we didn't know that this means that it's going to be out of bounds, we could actually go look at the type of int32, and we could see that the constraint is that it's limited in its size. Again, from like -2 billion to about 2 billion. And so the issue here is that low plus high could potentially overflow that variable. And we might ask ourselves, well, how can Daphne tell that this is going to happen? Yes?
I'm curious why it's highlighting the whole expression, not just the low plus high.
Oh yeah.
So I'm not sure. The highlighting is sometimes bad. Usually it doesn't actually line up, so I did have to adjust it on the slides to make it look a little bit nicer. I'd say it's still a work in progress.
It's because it does the intermediate calculations in an infinite space. And so the problem doesn't occur until it goes back into the int32.
Okay.
And in fact, the problem doesn't actually occur because you did it in an infinite space, and it is in fact in range. It's a false positive here.
Yeah. Well, this one could potentially be not a false positive because
it's legit.
Because if high,
it's a legit problem in the C++ code. It's not a legit problem in the Daphne code.
No, but int32, I think here is
int32 is guaranteed to be in the bounds of a 32-bit integer.
Yes, low plus high over 2 is guaranteed to be between low and high.
Yeah.
Oh, I guess I see it.
That's true. I see what you're saying.
It's a
Yes.
question if Daphne at runtime evaluates like the runtime evaluation of low plus high in an infinite space or in the int32 space.
Yeah.
Because if the runtime evaluation is in the int32 space, low plus high can overflow.
Yeah. Now, but my Daphne is not great, but I'm pretty sure the Daphne's idea is it's doing it in the infinite space, but it hasn't shown that it doesn't know enough about averages to pick that up.
Yeah.
Well,
I think
I think this first, where inside of the parentheses, I think is where the highlights should be. And I'm actually curious because like I said, the highlights, when you copy them over to slides, they kind of get mixed up. So let's actually go check this out. So I can show you guys, because I was planning on do this later anyway, so we'll just do it now. So if we bring this all the way over. Okay, is that too small, too big for you guys?
That's good.
Okay, it's okay? Okay, so this is our binary search code, and we'll kind of get to what all this stuff up top is in a little bit. But here is our statement that we're currently concerned with. So if we change it from this rewritten perspective to this perspective. Okay, so see in the IDE, it does give us the right squiggles. It says it's this expression. But then if we ask Daphne to verify it, and then we view our output. Oh wait, oh, I gotta save.
No errors.
I was like, oh, no errors. I just gotta save, and then it should show up now. Okay, there we go, one error. Yeah, so see, it kind of like, I don't know, it just highlights this part, and I honestly couldn't tell you why. So,
Are you using monospaced font?
yeah, I mean, I am.
I think it's about the right number of characters if it were shifted over.
I think it's like tabs are being expanded differently probably on different lines or something.
Yeah, so I don't know. I think I have spaces up here. I don't know if...
Or maybe your tab stop.
Sure.
Tab
Even
with
formal
different
verifiers
text.
fight over tabs versus spaces.
So to clarify, do we now think that they do operation in 32 or is it infinite space?
I think
In 32.
I think we now believe that they're doing it in the infinite
Yeah.
space.
Because high and low were declared in 32.
Yeah, so they're declared in 32. So this operation also... Oops, where are we looking at? So this operation... I don't know. That's actually a great question because I don't know. Because within these parentheses, I would expect it to return in 32, but it might consider that it's not. But I think based off of this, we can say that it is considering that whole expression within the parentheses as an int32 because it's giving us the error just for this portion right here.
What if you just add them to int64? Because in C++ you still get the overflow. You get two integers 32.
Mm-hmm.
You assign it to int64, it doesn't matter. Right?
Yeah, so what if we change these both to be int64?
No,
Now,
what
if
if
you change mid to int64?
Oh, if we change mid to int64? Okay.
Well, you will break everything, add another variable.
Yeah, probably.
Yeah.
If you change mid to N64, the high plus low still happens in the int space.
Yeah.
Well,
That
this
is a
the
way to
question.
detect if
This
it's
is the
happening in
question.
32 or in the infinite space.
Yeah, so we could check that. The problem is that I'd have to go and define a new N64 because Daphne, you got to define your own data types here. So we're living.
I might be totally naive, but is that complaining because high could be like the max and then low is 1 and then it adds together and then before it has a chance to divide, boom. So if you wanted to prove this, divide high by 2, low by 2, add them together, and then if it doesn't complain.
I think the rounding doesn't quite work that way.
Yeah, well, I don't know. As I said, it's naive. It's just
Yeah, no, that is. I think that is why it's complaining here. At least that's why it should be complaining. Like, my intuition says that's why it should complain here is because you could run into that situation where, low is 1 and high is int max, and then if you add them, oops, we accidentally went down to a lower number. And so, but yeah, we can fix this by just changing how we do our math here. So if instead we do high minus low divided by 2, and then we add low in, that is algebraically equivalent to what we did before. And this time it doesn't complain because you won't overflow in this instance. So if we come back here to the slide, something interesting is when we were looking at model checking has this very kind of step process where it looks at one state, it goes on to the next state. It looks at that state, goes on and so forth. So, but Daphne here was able to tell us that this should be an error. But if we just go backwards through our program, we might be confused as to why this is an error. Because if our low starts at 0, and if our high is a valid int32, then how does Daphne know that this right here might be an issue? And so what Daphne can do, because it's a deductive verifier, is it can say, okay, we're in a loop context right now. And if I consider what happens later in the loop, I can see that we are incrementing low. And so Daphne can imagine is kind of the word I use. That's not exactly what happens. But Daphne can produce a proof that says that there is a possible execution path, potentially, where I increment low, high is already int max, and then I experience this overflow on my next loop iteration. Yes?
Do I understand correctly is that when you program like this, every addition of two numbers is a problem?
No, not every addition. It depends on if it thinks that you can go over your bounds or not.
You can always add a precondition.
Yeah, so if you add a precondition, or even if you have a program where you assign like a concrete value to your initial state, like if you say like x equals 0, and then you add x to something, it can usually say, it can go through and it can prove well enough that, hey, I can see that you're never going to go out of bounds. Mm-hmm.
So I question the utility of this if that's what it's forcing, right? If you just have like a midpoint function and then you need to add a precondition that, low and high, whatever the precondition is, isn't that getting to the point to where it's becoming kind of nonsensical and too complex for programmers to deal with and think about?
Yes, but I think in this case, that's a good, I don't know, I don't have enough experience, I guess, to say whether or not it forces you to check every, algebraic operation. Because if it does, that is kind of a pain to have to go through and really constrain your inputs and your outputs. But I think it should produce a proof where it can get to a state where you could potentially overflow. Like this is a potential bug where it is possible that you could overflow your value here. But I'm not sure if it returns false positives.
So this is a sufficient problem that we're actually adding a midpoint function to the standard so that people won't write this. Also, there are techniques you can use to actually check for whether your arithmetic will give you the right answer. And if the library I proposed ages ago that you have in the Beaman queue ever gets approved, that'll be a lot easier.
Cool. Yes.
Maybe, I don't know if this is jumping ahead, but like, will this fire on the correct solution also? Like, will it think it'll overflow?
No. So if you change it to look like this, the error goes away.
Okay, so I guess it is smarter than just flagging every addition or something.
Yeah, so it doesn't flag every addition. And I would say that in my experience, it seems to do a pretty good job of only flagging true positives for arithmetic operations. There are other operations that it doesn't always flag a true positive. Which is actually a great segue. So now that we've fixed our arithmetic issues, it's going to look at this line and it's going to say that our index is out of range. Yes?
I just want to mention that bug you highlighted is a very, very famous bug. Like that midpoint being incorrect is a very famous bug.
Yes.
All right, good to know. Yes?
So it's interesting to me that it doesn't fire on this because high minus low can overflow. Does it know? Oh, because it knows it starts at 0. Is that why?
Yeah.
Yeah. Okay, that's fine.
It knows that low is less than high.
Yeah.
It knows that low starts at 0, low is less than high.
It knows that low is never negative. That's the thing. It knows that low is never negative. That's why it's not firing.
Right.
Yeah. So it can show that low will never be negative. I don't think it knows yet that low is less than high. Well, it should, because it's walking.
It doesn't show that low is never negative. It just fails to show any example where it is, and then it terminates.
Yes.
I see.
So and I guess no, it does know that low is less than high because we're in a loop right now. So Daphne can look at this loop here and it can say, my loop condition is that low must be less than high. So if I'm at that line of code, like you said, then low must be then less than high.
No, the less than is not sufficient. So if you have int max minus int min, you still overflow. The issue, what I'm saying here is that if it knows low is never negative, then it knows there's no overflow.
Yeah.
It knows that low starts at 0,
and
it knows that low only goes up.
Yeah, I guess that's true.
I assume it's established that. I don't know, but yeah.
Yeah. So that's something that like this actually is like a great kind of look into some of the issues that I've had with like using deductive verification is sometimes when you have like a success or a failure, it's hard to determine where does that success or failure come from, because Daphne in this case is just applying these proof rules, and sometimes it's not clear which proof rule did you actually apply here. And there are ways to try and extract that from the tool, and some are more successful than others. Here we get another error, and now that we fixed our arithmetic issues, it says that there's an error and that index might be out of range. And so it's talking about the index mid right here. And so what this is it's that Daphne is saying, hey, there must be a situation that you get to where you're accidentally accessing memory that you don't want to, right? Unfortunately, that's actually not true. So this algorithm doesn't read out of memory. But in this case, Daphne doesn't know enough to apply a proof to say that, okay, we are never going to be reading out of memory. So we need to give it some help. So, you know, in terms of how we give it help, there's lots of approaches that we could take. You could go through by hand, and you could say, you could try and figure out, okay, during each loop iteration, what can I guarantee holds with the relationship between low and high, and then how is mid calculated? You could go through and look at, you know, other people's solutions, see what they've found. But I've actually found that similar to what other people have said, is that AI is really good at helping in these situations because most Daphne code that is like on GitHub and out in the wild has successfully been verified, so it's correct. And so what I did here is I asked Gemini, the integration into VS Code, I gave it the error message, this one that we see here, and then I gave it the line, and I said, hey, can you fix this for me? And so what it did is it added a loop invariant to this loop right here. So what a loop invariant is it's a formula that holds for every iteration of our loop. So for every time we iterate through our loop, this invariant, we can always show that it holds to be true. So what our invariant says here is that low and high are always greater than 0, and that they are always either ordered, that low is less than high, or they're equal to each other, and that we are not going outside of our array bounds. Yes?
Is this array as inserted to cast will cause you problem inside the invariant if you're, like, given that the array can be big as an inserted to?
No, so this doesn't cause an issue, but that just comes back to earlier when we had this error. We told Daphne that was okay. And I can show you how we told Daphne that it was okay. And what I did to get rid of this error is I said, hey, I don't want to deal with this because this isn't exactly the error that I wanted to look at. But because to fix this, we just have to change the types, or we'd have to change the precondition to indicate that our array is never going to overflow an int32.
Oh, interesting.
Mm-hmm.
Good question. Is there a chance that actually array as int32 would be a negative here, or does it understand that it can't be more than like long? What is it, max? Or because when you cast a long to it or long to an int, you could get a negative number.
That is a good point. So yes, it understands because Daphne does do computation on an infinite domain usually. So when you actually get the length of your array, that length can be anywhere from 0 to infinity. And so because we're not really looking at bits per se inside of Daphne, when we cast it to an int32, it's just saying, okay, it's a number within the range of int32.
Yeah, Daphne I don't believe has the same semantics as a C++ cast.
Yeah.
So what does it mean in Daphne if you say as int32 for something that's bigger than int32?
It's actually adding a constraint. It says I'm asserting that this thing satisfies.
You are not allowed to do the cast.
Yeah.
Okay.
So if your value could, like in this case, our value can, and like I said, I told Daphne that was okay. But if your value can go outside of the constraint of int32, then it just won't let you do the cast.
Yeah, and the reason why, if you told it for the above that it was okay, then it knows like, oh, okay, then this must fit, so therefore this cast is also fit.
Yeah. And that was just because if we don't change that, then we just have to change a lot more things. And I wanted to focus on a couple of the small bugs in this implementation. So something that's interesting here is that we just have to add this invariant, and this gives Daphne the information that it needs to prove that our loop is correct and that we're never going to that mid is never going to be an index outside of our bounds. And so now that we've added that, Daphne is happy with our function. It says, okay, this function looks great. Yes.
Do you think we could remove the middle, low, less than equal to high, given that we have it in a while loop?
I don't know. We could actually find out. Let's see here. So if we come back to VS Code. Okay, so if you're saying just remove.
And, do an and in between those two instead of less.
Oh, so wait, sorry, say that again. So do like and between where?
Here, after low.
Like that?
And
Yeah.
then get rid of that. Yep.
Get rid of that? I don't know, let's find out. It's not giving any errors in the IDE, so I think we're good. So yes, that would also work.
Alright.
So yeah. Alrighty, so from here, what we want to do is we need to add our pre and post. So this is all before we've even added our pre and post conditions to this function. So this function doesn't even know that array is supposed to be sorted. It doesn't know what it's supposed to return. We don't have any guarantees about that. So now we're going to go through and we're going to add these into our function. So the way that you introduce pre and post conditions in Daphne is after you declare the function, you can either put requires clauses, and that indicates a precondition or an assumption that you make over this function, or you can add an ensures clause, which means that that's a post condition that Daphne will check that it should hold. And if it doesn't hold, it will give you an error. So first we have this precondition that declares that array should be sorted. And I'll show you guys how we implement that in Daphne in a second. But basically, I mean, it's just a isSorted function checking that every value is sorted with respect to its neighbors. And then we also add our post condition, which is the same one we derived earlier. And we're using exists here. That's just a keyword in Daphne. It does the same thing as the mathematical notation would do. And then we also, just encode our property here, kind of in a pseudocode, pseudo-mathematical notation that Daphne recognizes to add this to our function. And you can see that one thing that Daphne has that C++ does not have is the implication operator. This font turns it into a long arrow, but it's really just two equal signs followed by a caret. Yes?
So when you have multiple ensures, is there like an and? Do we understand this as an and?
So that's a great question. So sorry, I totally forgot to mention that. So here we're starting each line with the double bar, which is the or. And so in this case, this whole statement is ORed together. If we wanted to and them all together, we could just do two ampersands next to each other.
So,
I mean, don't you want this to be and though?
Yes, we do. That was what we determined earlier, that I wrote this incorrectly, unfortunately.
So as he originally specified it, it was either it points to the thing or it points to size.
Yes.
And so that's what he encoded in that ensures.
Yep. So yeah, we've encoded this here in the ensure. So the or, the upside down caret or operator in Daphne, you do it with 2 bars. And it's kind of weird because in this instance, it's being used as both like a unary operator and a binary operator. So we put it before a statement. And then if we just have one statement, it doesn't do anything. But then if we have multiple statements, it acts as an or between all of the statements. And I think they just do that because of like mathematical notation. Sometimes in papers, you'll see that if you have like a bunch of conjunctions or a bunch of disjunctions, you'll have them all aligned vertically in order to indicate that all of those statements are ORed together or ANDed together.
I think it's actually a bit more like some people like to have that extra trailing comma on the last thing in the list because it makes it cut and paste easier. This way you get the same thing at the beginning and it cuts and pastes easier.
That's a good point as well. So yeah. Yes?
On that note, what would happen if you had ensures and then the next one was or? Like, what would that mean?
That will just be like a compilation error.
Okay.
It will just tell you, hey, you can't use these operators together. So you can like nest them together like using parentheses and stuff, just like you would in C++. But if you do something like, if you have or and then and, it will say, I mean, that will be like, it'd have a hard time determining, should I do the or, should I do the and? So it'll just be an error.
I still have the questions that David had. Like, it seems to me that if I exists, then anyone, and if I doesn't exist, do the other thing. Why is the preconditions or?
Yes, it should be and, because I just wrote it incorrectly. And I
Okay,
didn't have someone
gotcha,
review my
gotcha.
slides. So, yep. The function body is just unchanged. It's just the same function body. So, although in this case, we know that our answer is not right because we wrote our insurers clause wrong, to verify this, you just call the command line tool, Daphne verify, with your file, and then it will either give you the errors like we saw in the examples earlier, or it will just tell you that it's verified your code. And so if we go back to VS Code, so kind of as I showed before, let's see here, here's my cursor. We also have like IDE support here. So in VS Code, it's got these nice little check marks and it's really interactive. So if you're writing your code and you run into an error, it will tell you usually the line and the statement, the expression where your error occurs, and you can try to fix it right there live in the editor. So just to show a couple of things that
Didn't we figure out that that's the wrong insurer specification for this method?
Yes.
Yeah, which is the only reason
Did
why it
Daph-
passes.
Yes.
So to clarify, if you change it to end, that will catch the bug.
Yes.
Yes.
So if I change this right here to, yep, now I'll just say a post condition cannot be proved on this return path. And then you can actually ask the command line tool to give you a counter example as well.
Oh, let's ask it.
All right, we can.
This is even better than correct code. No, for real.
Yeah.
See? This was planned, you know? No. All right, so let's go ahead and I think,
Still need to say.
let's see here. I thought I already had it here, so we're going to do,
You still need to say.
Contract wrong.
okay. So we just do Daphne verify, and then we're going to just ask it to extract a counterexample. And so counterexamples in Daphne are actually not that great. So a couple things with counterexamples and with deductive verification overall is that because we're applying proof rules and we're trying to compose these formulas together, that means that we can sometimes run into logical contradictions that the proof system kind of introduces. If we don't give it enough information about preconditions, then it can kind of imagine, again, my word for it, it can imagine a state where, hey, you started with your array of this length, and you might be like, well, that's not possible. So then in that case, you do have to go in and add some more preconditions. But basically what this counterexample is saying is it's going to give us a list of different states. So at each of these places where it gives us a line of code, it's going to say that after this line of code, these are the concrete values that are assigned to all of your variables. And somewhere in those values, your post condition could not be proved. And so you can go through and you can parse these out. I wrote a little Python script that goes and formats this nicely. So I know kind of a lot of work on top of a lot of work already. But I wrote a Python script that formats these nicely and finds where your contradictions are and where the errors happen. And yeah, this is an area where Daphne is currently improving a lot. People are contributing a lot to this. So really quick, because I believe I only have a couple minutes, we are just going to go and finish really fast. So now what? We've kind of given an overview of how formal verification kind of works behind the scenes. We've talked about some basic principles, some mathematical notation. And so hopefully from here, you guys have the knowledge to go forward. And if you want to explore these topics on your own, you can, get started doing that. So after this, I have kind of 3 considerations that I think you can make. So the first consideration is if you want to apply formal methods to somewhere in your code base, I would consider starting somewhere small, which I guess, is very clear. But for example, Malta gave an example of fixing a glibc bug in their condition variables, and that is pretty big. But if you just find somewhere small where you can say, okay, I think this core algorithm or this core function I can verify, you can go and you can use tools to do that. As a tip, I guess, if you're doing any kind of verification of generics or verification of algorithms, Daphne is probably going to be your better tool. Whereas if you're doing verification of a function that has more constrained inputs, if you're doing like embedded or something, you're looking at sensor inputs or something like that, model checking probably would work fine and will probably be a nicer process to work with overall. So the second thing is that we can learn from formal methods to write better C++ code. And so just like the model checker deals with state explosion, we also sometimes deal with state explosion when we're trying to reason about our code, when we're just working through it in our mind. And so something we can do is we can introduce constrained types or behaviors into our code bases in order to make it easier to reason about. Jeff's talk yesterday, I thought was kind of a good example of this, where to eliminate some memory bugs, they said, hey, we're going to constrain the types that you can use. We don't want you to use pointers as much. We want you to use these other types, these reference counted types, and in order to try and eliminate those bugs and make it easier to reason about where they come from. From deductive verification, deduction is really compositional. In a sense, you could say that every statement in a deductive proof is composed together. And so it just shows how important composition is. And my final third idea for you all is that you should all go out and check out a formal verification language. You can check out Daphne if you want to do a more kind of traditional programming language approach. You can check out TLA+, which looks more like it does parallel reasoning. There's other languages that you can look at. And I think similar to what some people have said about learning a functional programming language, if you write in a formal verification language, you kind of start to get a sense of, okay, what's easy to verify, what's not easy to verify, where do my issues arise, where do my issues not arise? And then you go back to writing your C++ code, you can apply that intuition back into your code bases. So I also have some resources. If you're interested in learning more about program proofs, there's a book, it's called Program Proofs, and it's just it's technically a textbook written for undergrads, but I think it's a great introduction to how you might prove stuff about programs. And yeah, it's just a great introduction. It has lots of good examples, real code, all that kind of stuff. There's links here for these two model checkers, the C and C++ ones, and then a link to Daphne, some mathematics definitions, and then I also have a personal blog, and that's where I will post the slides, hopefully with a corrected post condition. And I think that's all. Do I have any questions? Yes, Sean.
Just a short comment, which is Daphne can compile to other languages, several other languages, including C++. So you can write Daphne and generate a library, a C++ library out of it.
Yeah, that is a good point. I guess something we didn't cover is how do you handle, if you're doing your verification in two different languages, how do you handle that? One of the things Daphne is nice at is that you can kind of export it into C++, which is nice. Yes.
So I think that the fact that there was an issue with the code that you showed is actually a great segue into my talk tomorrow about correctness.
Yeah.
But it does raise the question on a practical level. People may want to adopt Daphne, right? And they may want to use AI to write the code because why wouldn't they?
Yeah.
Is there a danger of getting a false sense of security that, oh, this is Daphne proven correct code, and actually there's a bug in the preconditions or whatever, and you would never think that because it's like you walk away thinking that your code has been proven statically.
Yeah, there is a danger with that. I think, so I don't have like a ton of experience, I guess, in working on big code bases, but in my experience at school and with research, we do run into that where you might produce some results for a research paper where you formally verify a system, and then you realize after you've written the paper and the results and submitted it, you go, oh, hey, I actually messed up one of these conditions. And so there definitely is that possibility. And still, even if you're using like a formal tool, it really comes down to how do you produce correct conditions here? How do you produce correct preconditions, post conditions? without introducing errors. So yeah.
I think
Remember Knuth's,
I was just thinking that.
I have only proven this code correct, I haven't actually tested it.
Yeah.
My advisor used to call that incorrect by construction.
Yeah.
I mean, the general rule there is it's like, my analogy is usually from accounting. It's double entry bookkeeping, and it's like, you know, you do it two ways, you do it in two different ways, and you get the same results. Your confidence level goes up. It doesn't mean there isn't an error. It just means that if there is, it's counteracted on both sides.
Yep.
Right.
But then it also gives you the property that if you catch your error in your specification and then fix the specification, you now have the power to prove all the other bugs you have not meeting the correct specification. Like there's no, you don't have to apply that stuff in your head.
So how much C++ contracts can be used to verify things?
I have heard, I don't know a lot. So I've heard that it will give compilers nicer tools to do static analysis, but from my understanding,
Perhaps people who know things.
I was going to say, other people are welcome to contribute because I don't know.
I can't say for sure how it's going to interact with these tools because I don't know the future of these tools. But the fact that you had to write all of your pre and post conditions separately from your code in a different language is a real issue for using these tools. If you are writing your pre and post conditions in the same language as part of your code and also using those same conditions as part of your tests, you have a leg up and it can feed into these sorts of tools.
Yeah. An interesting thing with contracts is I haven't seen anything in the proposal that says here's how you would have an existential or a universal quantifier.
No, we have nothing, but we can say here's how you would have a loop. And it turns out that loops look a lot like a quantifier in some ways. Also, template parameters look kind of like quantifiers sometimes, but it's more like a schema. But no, we have no actual quantifiers. We just have things you can use in place of quantifiers.
I'm just trying my loop from negative int min to.
Yeah, but
and then it's the
particularly
compiler's job to make it work.
for example, in here the things about being sorted were expressed as quantification, but they didn't need to be. They could have been expressed as loops.
Yeah.
Yes, although that makes a theorem prover have to, because it's not going to run through each iteration, so then it needs to back derive what the quantifier is from the loop. So.
Yeah.
There were axioms at some point, right, in proposals?
What's that?
There was at some point in proposals for contracts or for some other things, there were axioms.
The thing that people were using the word axiom for in contracts related things, that is a weird use of the word axiom.
Cool.
Why is it called a ghost predicate?
That's to make sure it never gets compiled. So in Daphne, if something's a ghost, then it won't ever emit code when you run it.
I just thought it was scary.
It is pretty scary too. That's why. Yep. So, all right. Any other questions? Cool. Well, thank you all for coming.